Hello everyone, today we'll be starting with number system. So you must all be imagining that what is something new that we'll be learning about numbers, because this is something numbers that we have learned from childhood since we started learning arithmetic. So it is an integral part of mathematics. So let us start, like, where did we start learning numbers from? We started learning numbers from our early childhood when we started with counting. Yes, when we started counting objects and we started with counting numbers. So what are these counting numbers? The counting numbers, they begin from 1, 2, 3, 4, so on till infinity. These set of counting numbers, we grouped them and we taught you as a group of natural numbers. Then gradually we discovered that our bags can be empty, a bag full of chocolates, and if I empty it, then no chocolate is left. Then how do we term that empty thing? Then came the concept of whole numbers, which along with the natural numbers has an element 0 with it. So initially we started with natural numbers, then whole numbers, and after whole numbers we came to a different world of negative numbers. Along with whole numbers, we learnt about negative numbers also, a value less than 0. So representing all these numbers which we have learnt so far on a number line, 0 being in the center of the number line, we have the positive numbers whose value greater than 0 lying on the right of the number line, and the negative numbers on the left of the number line. And the two arrows, they represent that the number line extend itself towards infinity, both on the positive as well as the negative side. So these are my negative numbers, and here to the right of 0 we have positive numbers. So this entire group of numbers, positive, negative as well as 0, they were grouped as integers. So we started with natural numbers, a bag of natural numbers containing the counting numbers. To it we incorporated an element 0, and my bag became bigger and it became a set of whole numbers. Now further we studied about integers, which included negative numbers also, and since we have a group of negative integers now, the bag will take a larger size and the integers will be represented by z and the bag will become bigger. So gradually we can see the evolution of number from natural numbers to whole numbers to integers. Along with this, we've also learnt about fractions and decimals. Decimals are nothing but a way of representing fractions on a number, on a place value chart. So all these numbers together, which we have studied so far, they are grouped under rational numbers. So basically what we'll be studying in this chapter, what we'll be discussing here is are the rational numbers, which include group of natural numbers, whole numbers, integers, fractions and decimals. Then if these numbers are rational, then there are other set of numbers which do not fall under this category, and that we are going to discuss in detail is the set of irrational numbers. Both the rational and irrational numbers, they are grouped in a common set of real numbers. Then we'll also study the representation of real numbers on a number line, and then we'll also study about some exponential or index form of numbers which involve law of exponents. Now, starting with representation of numbers on a number line. As we can see, and as I've told you earlier, this is a number line denoting the positive as well as the negative integers. 0 is the central value, and to the right of the number line we have the positive values, and to the left of the number line we have all negative values. So basically a number line is a horizontal line where we represent 0 along with positive and negative numbers, which extends indefinitely in both the directions. Natural numbers, they are represented on the right hand side of the number line after 0, and they are also known as counting numbers. Whole numbers, numbers that include natural numbers along with 0. Then we came across integer, which includes whole numbers, natural numbers and negative values. See, these negative values, they are also known as directed numbers. Now, why do we call them directed numbers? Because these negative values, they are just indication of direction. For example, if I tell you move 5 steps, my sentence would be incomplete. But if I give you a direction, move 5 steps to the right or 5 steps to the left, then my instruction would be complete. Similarly, on a number line, if I say 5 steps to the right, I am indicating positive 5. But if I say 5 steps to the left, I am indicating negative 5. That is why integers represented by z, they are also known as directed numbers. Now, coming to rational numbers. What are rational numbers? The numbers that we have studied so far, the natural numbers, the whole numbers, the integers, fractions and decimals, they are all grouped as rational numbers. So when I am saying a set of rational numbers, what does a set mean? A set means a collection of well-defined objects or numbers which belong to the same group. So why would I say that whole numbers, integers, natural numbers, fractions and decimals, they would belong to the same group? Because they have a common characteristic. What is the common characteristic? For example, if I start with a natural number 1, can I write 1 as 1 upon 1? Yes. I can write 1 as 2 upon 2. I can write 1 as 3 upon 3 or 1000 upon 1000. Similarly, if I choose any other natural number, for example, if I choose 5, 5 can be written as 10 upon 2. 5 can also be written as 25 upon 5. This is all about how we can represent a natural number in the form of a numerator upon denominator. But provided the numerator can be any natural number, or it can be any natural number, but the denominator cannot be 0. Denominator cannot be 0. In that case, I'll not get any defined value. Now let's take a whole number. Starting with a whole number 0. 0 is the only exclusive whole number in the set of whole numbers and natural numbers. So, can 0 be represented in the same way as we have represented a natural number in the form of numerator and denominator? Yes, it can be. I can write 0 as 0 upon 1 or 0 upon 5 or 0 upon 100, because 0 divided by any number will give you 0 only. So we have seen that a whole number can also be represented in the form of numerator upon denominator, where the numerator can be 0 but the denominator cannot be 0. So what is a rational number and how do I categorize it now? As I have seen, a whole number can be represented in the form of numerator upon denominator. Natural number can also be represented in the form of numerator upon denominator. What about an integer? Let us see. Let us consider an integer minus 3, a negative integer, because positive integer we have already taken the natural number. How can I write minus 3 in the form of numerator upon denominator? I can write it as minus 3 upon 1. I can also write it as minus 6 upon 2. I can write it as minus 75 upon 25. Again, I can see that all the negative values or the negative integers can also be represented in the form of numerator upon denominator, denominator not equal to 0. Talking about a fraction is already in the form of numerator upon denominator. If I am talking about a decimal number, for example 7.5, it can be written as 75 upon 10. So what is the common characteristics that we have studied so long? The common characteristic of all these numbers is that each one of them can be represented in the form of numerator upon denominator, provided the denominator is not 0. So there comes the definition of rational numbers. So what are rational numbers? A rational number is a number that can be represented as P upon Q, in the form of P upon Q, where Q, the denominator, is not equal to 0. And the symbolic representation of a rational number is by the alphabet Q. Now, we have already studied what are rational numbers, and you must be thinking that we have covered every number that we have studied so far in mathematics. Then what is a rational number? I told you in the beginning that numbers which are not rational are irrational numbers. You must be thinking that which are those numbers which are not rational, because we have only studied these numbers so far. What defines a rational number? A rational number is a number which can be represented in the form of numerator upon denominator, provided the denominator is not 0. Then obviously irrational numbers are those numbers which cannot be represented in the form of numerator upon denominator. And when is that possible? When is that possible? Let me show you. For example, if I take a decimal number 7.5 and if I represent it in the form of P upon Q, that is numerator upon denominator, I will write it as 75 upon 10. It has a proper denominator, a definite denominator. Why? Because the digit after the decimal point is finite. It is terminating. Even if I write 0.25, I will have denominator as 100, because we have 2 digits after the decimal point and it is finite. But what if I have to represent 0.21357 ... We cannot decide the denominator. We cannot decide the denominator because the numerator, the decimal placement is infinite. There are infinite number of places after decimal and there is no pattern followed and we do not know where will the number end. So even if I write the numerator 2, 3, 5, 7, 9 dot dot dot, I cannot decide that in the denominator how many zeros I have to place. So in this case, it cannot be represented in the form of P upon Q. This defines an irrational number. So what is an irrational number which cannot be represented in the form of P upon Q? We'll learn more about irrational numbers, that where do we get these irrational numbers. So a number S, so the representation or symbolic representation of an irrational number is S, symbolic representation of a rational number is Q. So a number S is called irrational number which cannot be written in the form of P upon Q, where P and Q are integers and Q not equal to 0. They have given you the examples, root 2, root 3, root 5. What are these root 2, root 3, root 5? They are all non-perfect square numbers. So all the imperfect squares and imperfect Q along with the value pi. Pi is an approximation. The value of pi which we use in mensuration and geometry is an approximated value of a irrational number. As we can see, 0.2110, we cannot even observe the pattern. There is no pattern involved, and it is infinite placement of decimal values. The decimal values are going infinitely. So that is why it is an irrational number. So what we have learned, that a number is either rational or irrational. So the rational and the irrational number together, they are grouped as real numbers. Because why are they real numbers? Because they do exist. As I am using the word real, in your higher classes you will also learn about numbers which are not real. But that's a later part of the story. Every real number is represented by a unique point on the number line. Yes, even the irrational numbers can be represented on a number line, and we have techniques for doing that. Every point on the number line represents a unique real number. The real number is the real number line. So the number line which we will be discussing now is the real number line, because all the real values of the number can be represented on that line. We have a number line on which we represent the numbers which are not real or the complex numbers, but we'll be studying for the time being the real numbers. Finding, as I told you, that on a number line we can represent infinite number of rational numbers. If I ask you a question that how many rational numbers can you fit between two rational numbers 1 and 2? If I give you two rational numbers 1 and 2, and if I ask you a question, how many rational numbers can you fit on the number line, if it's a number line? If on a number line, if I give you two numbers 1 and 2, and I ask you what will come between 1 and 2, think. Yes, it may be little difficult for you to think what would come between 1 and 2, because you are not thinking about rational numbers, you are just talking about, or you may be thinking about natural numbers. But why do we forget that between 1 and 2 we may have decimal values like 1.2, 1.3, 1.99, and even if I divide it further into very minor segments, I can have 1.001 as well. So there are infinite values. There are infinite numbers, or infinite, I would say, rational numbers that can be fitted between two rational numbers. So that would be our next topic. Let us see how do we fit the infinite rational numbers between any two given rational numbers. Suppose I have two rational numbers. I've shown you with example of 1 and 2. But if we generalize it, how do we generalize it? If I have two rational numbers r and s, then and how many rational numbers will be there in between? Infinite. Then between r and s, if I have to put one particular value, suppose my r is 3 and s is 4. Then between 3 and 4 on a number line will come the mid value of 3 and 4. The mid value of 3 and 4, and it's very simple to calculate. The mid value of any number is given by the sum of the numbers divided by 2. So the mid value of 3 and 4 will be 7 divided by 2 equal to 3.5. So obviously, if I have to fit one rational number between two given rational numbers, it will be the mean value. Mean value is the average value that is obtained by adding the two numbers and dividing it by 2. But what if I have to fit more than one rational number between two given rational numbers? Like here, they've asked you that find three rational numbers between 2 and 3. But you may ask me that I've just told you how to fit one rational number by finding the mean value. If I had to find one mean value between 2 and 3, I would add 2 and 3 and divide it by 2. But what if I have to find more than one value? Let us do it with the help of a number line first, and then I'll explain you the technique. This is 2 and 3. And the mid value we can find out. We know we can find out one mid value, that is adding the 2 and dividing it by 2, and between 2 and 3 I know the mid value will be 2.5. But this is just one value. Two more values can be inserted here and here. How? By considering this also as a part of the number line now. Previously I had two values 2 and 3, now I have yet another value 2.5. So if I have to insert two more values, I will take the mid value of 2 and 2.5 and one mid value of 3 and 2.5. By using the same technique, previously my r was 2 and s was 3, from where I got the third rational number 2.5. Now my r is 2 and s is 2.5. So the next rational number will be adding these two and dividing it by 2. So 2 plus 2.5 will give me 4.5. 4.5 divided by 2 will give you 2.25. Similarly, 5.5 divided by 2. 2.5 plus 3 will give you 5.5, and 5.5 divided by 2 will give you 2.75. Thus we can have three rational numbers which can be fitted in a number line between two given rational numbers. In the similar way, we can have infinite. Between these two values also, I can have two more values. Between these two, I can have two more values. So there are infinitely many rational numbers between 2 and 3, or between 3 and 4, or between given any two rational numbers. Those two rational numbers need not be a natural number as shown here. They can be a decimal number also. For example, if I take 1.5 and 1.6, between 1.5 and 1.6 also I can fit infinitely many rational numbers. For example, if I take decimal number 1.5 and 1.6, then also in between these I can fit as many rational numbers as I want. The same technique will be followed. Method 1 is the method that I have just told you, that divide by 2, the sum of the two numbers to be divided by 2. The sum of the extreme values divided by 2 will give you the mid value. So as we can see in the example, if I have to fit a rational number between two rational numbers 2 and 3, add the 2, divide by 2, and we can get as many rational numbers as I want. Method 2 is less tedious than method 1 and it's quite simple. What is method 2? If I go by the same example that I have to find rational numbers between two given rational numbers 2 and 3, I have to write the rational numbers in the form of numerator upon denominator. So 2 can be conveniently written as 2 upon 1 and 3 can be written as 3 upon 1. What next? Next is counting how many numbers do I want. So here suppose I have to insert 3 rational numbers between 2 and 3. So what would I do? I would add 1 to the total number of rational numbers which I require. If I require 3 rational numbers between 2 and 3, then I add 1 to 3 and make it 4. But what to do with this 4? I have to take this 4 as the denominator of the given numbers. I have to convert the denominators of the given number to 4. So, according to the examples which is shown here, 2 was previously written as 2 upon 1. 2 was written as 2 upon 1. Now, if I have to convert the denominator of 2 to 4 using the law of equivalence of fractions, I have to multiply the numerator and denominator of 2 by 4. To make the denominator 4, I cannot simply only multiply the denominator by 4, I have to multiply the numerator also with 4 and it will give us 8 upon 4. Similarly, 3 can be written as 12 upon 4. Now, let us draw a number line. And this is my 2, this is my 3. I have 2 is equivalent to, I have converted it to 8 upon 4 and 3 has been converted to 12 upon 4. Why this 4? Again I am reminding you, again recalling that we make the denominator equal to 1 more than the number of rational numbers required to be fitted in between the two given numbers. So, I have to insert numbers between 8 upon 4 and 12 upon 4. Let's think that way, that we do not have to insert numbers between 2 and 3. We have to insert it between 8 upon 4 and 12 upon 4. Now, focus on the numerator 8 and 12. Between 8 and 12, I have to mark all the numbers between 8 and 12 on this number line. So, after 8, I will have 9 upon 4, then I will have 10 upon 4, then I will have 11 upon 4. So, we have got all these 3 numbers very easily. So, the numbers between 2 and 3, the 3 rational numbers between 2 and 3 are my 9 upon 4, 10 upon 4 and 11 upon 4. These are the 3 numbers between 2 and 3. So, basically what is the idea? The idea is just to convert the denominator. And how do we convert the denominator? We convert the denominator by making the denominator 1 more than the required number of rational numbers. So, if 3 rational numbers have to be inserted, we make the denominator 4. Had 4 rational numbers been inserted, we should have made the denominator 5 and so on. So, if n rational numbers have to be inserted, if we were supposed to insert n rational numbers, then the denominator would have been n plus 1.
To watch the complete video, download the Upbind educational app from Play Store and App Store.